to people who might be interested, namely that I'm organizing dinner tonight, if anyone wants to join us. And I think it would count as the usual dinner out the center speaker, even though it's 4 days late. So that would mean grad students would get the subsidy. Undergrads could probably work something out, and grad students. So anyway, check your email and reply to me, and I'll by email figure out where to go and or we can just talk after class. Who's still leaving tomorrow? Okay, but you'll be with us by YouTube. And the rest of it. Also, in that regard, I was thinking Monday, let's spend the whole day talking about exercises. Okay, so whatever you've managed to think about, and we can shut down the video if it makes it more comfortable. We don't need to record it on your broadcast, right? Unless you want, we can decide what to do. So think back and spend the weekend sort of collecting your thoughts, whatever efforts you've had or half-baked ideas you had or so on. We'll try and give most, anyone who wants to say something, a chance to say something. Okay, so what am I doing? I'm thinking about, the question at hand is if we have a critical point, so consider two critical points. I was calling PI and PJ, but let me call them P and Q. Okay, critical points P and Q in X. X is always my domain. I have a Morse function on it, right? Let's assume that, so let's say f of P less than f of Q, and no critical points in between, no critical values in between. And then I want to, so we choose an adapted metric to the Morse function to give it, and therefore, we get a vector, a gradient flow, and therefore you get ascending and descending manifolds. You get the ones I'll just say it. You get ascending and descending manifolds. Okay. And then I want to ask the question: what? Let's think. So consider. Well, I'm really interested in understanding the ascending manifold for the lower one and descending manifold for the higher one, and whether or not they intersect. Okay, so does a ascending manifold for P intersect the descending manifold for P? And so the way to think about that is to take if they do intersect, then they'll intersect. So in between there's no critical values. In between there's no critical values, so I've got this from f of P plus epsilon up to f of Q minus epsilon, everything looks like a product. So if they intersect anywhere there, they intersect in a level set, and then the intersection persists. So I just reduced to the case of, considering f inverse of t, for t some f inverse of t, where t is a regular value, so between f of p and f of q. And I want to look at the intersections of these guys with that, and then I sort of wish I had some good name for those. Maybe I will. I'll come. Okay, so let's take. Let's let ascending p. I'll just put superscript t. Okay, this is going to be ascending manifold for P intersecting with f of T, and similarly descending manifold for Q, superscript T is dq intersecting with f of T. And the first thing is to notice that these are spheres, okay, of appropriate dimension. So why is that? Well, actually, before we do that, let's remember what the dimensions of these manifolds are. Okay, and to do that, I need to tell you what the indices are. So let's say the index K equals the index of P, and L equals the index of Q. And then therefore, DAP is diffeomorphic to a, well, the whole ascending manifold. Let me put it this way. Maybe we should just take the canonical picture to help our intuition. Question?
Oh, sorry.
Tell the answer. So, but I need two critical points here. Put another one up here. Okay, so I have, I'll draw where they don't intersect. In this example, descending manifold, I no consistent color codes, ascending manifolds, but all I care about is, this is P, this is Q, all I care about is this ascending manifold, this descending manifold, and then I take some level set between, T, okay, and the point is this ascending manifold is, up to any level is a disk, at least until it runs into another critical point. Okay, so this is, if I take first of all, the dimension of the ascending manifold for P is n minus k, n is always my total dimension, and then the dimension for the descending manifold for Q is L, and so therefore A sub P T is diffeomorphic to a sphere because this is this ascending bit is a disk because I haven't run into anything else, right? And so the ascending manifold for P intersected with level T is going to be a sphere of dimension n minus k minus 1, and the descending manifold for Q at level T is going to be diffeomorphic to a sphere of dimension n minus 1. Okay, any questions on that? In this case, in that picture, we're both zero spheres. Should be a number should all work out right there. And let's also remember what the dimension of the whole the ambient space. So now these are submanifolds inside. Now I don't want to think of them inside of X. I want to think about them inside F inverse of T. So the dimension of F inverse of T is equal to n plus 1. So the first observation that I want to say is that by this observation, any isotopy of either one of these, any isotopy of A sub PT in F inverse of T can be realized by, I would say homotoping, or I'm just saying by modifying G below level T, so T on F inverse of, actually it's F inverse, to be very precise here, F inverse of T minus some epsilon, minus infinity up to T minus epsilon. Actually, I can be even more precise. So let's say T minus 2 epsilon, T minus epsilon. This may be useful to know. Okay, so what do I mean by that? What I mean is, if I look at the ascending, so I'm going to call this the ascending sphere. The ascending sphere inside this level set. And I want, for some reason, to isotope it around, to move it around by some isotopy. Okay, so I can what I want to do is I want to change the vector. I want to change the metric so that the vector field changes. So that if I want to take a one-parameter family of metrics, giving me a one-parameter family of vector fields, giving me a one-parameter family of ascending manifolds, so that the ascending spheres move by that isotopy. Okay, and so if you think about it, when you're moving the sphere around, then you've already got a product structure. So you can, it really boils down to just saying inside a sphere across, inside the ambient space across an interval, if you want to move something around, well, that's an ambient, the real point is isotopy extends to ambient isotopy. And an ambient isotopy can be realized as the flow by a vector field on product cross manifold. And then, so it's sort of clear from, so ambient isotopy implies ambient isotopy. Remember, ambient isotopy is when you're moving the space things are embedded in. It implies ambient isotopy, and that implies there exists a sort of a one parameter family of vector fields. And you can do it, I mean, everything's a product. I want to do it in some level set here. So originally my vector field went up, straight up like that. And now I'm going to modify it, tilt it over a little bit so the flow realizes that ambient isotopy. So you get one parameter family of vector fields. And then, as we discussed before, these are vector fields that are getting transverse to level sets. Any vector field transverse to level sets can be sort of promoted to a metric, so that that's the gradient vector field by declaring it to be perpendicular to the level sets. So that gives a one parameter family of metrics. I know it's sketchy, but we'll see if I take questions rather than give more details.
I mean, it doesn't seem clear that there's not some isotopy of this sphere inside the level set that sort of would have to go like down. I mean,
and then the sphere moves in the level set, but you sort of to get from, and the sphere itself
it
is moving
because it's in the level set,
right? And so basically, you've got let's just imagine a circle. Actually, just imagine a point, right? You've got a point moving around in your space, right? It has, another way to say it is there's a track for the isotopy, right? And you just, the point used to be, so here I've got a point below that's supposed to flow up to here, right? And now I want it to, instead of flowing up to here, to flow over here. And I want to do that in a one parameter way. Well, this goes along here, so then as I go from 0 to 1, I modify the vector field. I have to make a one parameter family of flow. What I really have to do is construct a one parameter family of flows first, and then take the derivative of those flows to get the vector field, and then reconstruct the metric so that those vector fields are perpendicular to level sets.
But because the sphere is stuck inside this level
exactly.
set, then you don't ever have to worry about
That's right.
like going through non-transverse.
Exactly. And I'm only, that would be a much different situation if I was allowing the sphere to come out of the level set directly. And so the upshot is and the reason I wanted to say I can do it below, well, I could have just said I can do it just below, but the reason I wanted to sort of localize it to one thing is I want to move this one as well by some isotopy in some level set above it. Okay, so similarly, for the descending manifold, the descending sphere, the QT, modification in modifying things in F inverse of T plus epsilon and T plus 2 epsilon. So you stay away from critical points, you just stay, everything's this little neighborhood, right? And so the point of that is that I can move them around, I can move both of them around arbitrarily by isotopies in this level set. And if that helps me at all, think about this intersection that's good, in particular if I want to eliminate intersections, for example. And so now I want to say that, so I want to use transversality and argue that. So the point is I can whatever, I can arrange, therefore I can assume that actually, maybe I should also say any any perturbation, let's just say that is of G, moves these spheres by an isotopy. Moves. That's perhaps I should have said that first. If you perturb G any way you want, that'll just move the vector field continuously smoothly, and therefore move the flows smoothly, and therefore move the ascending manifold smoothly, and therefore move the intersections with the level set smoothly. And everything will remain embedded throughout because there are always ascending manifolds for some. I say perturbation through adapted metrics, and that's one reason why I asked that question about connecting to adaptive metrics by adaptive metrics. And so, so therefore, what I want the upshot of this is we can always assume that they intersect transversely. Are you happy with this notation? This means transverse intersection. Okay. And transverse, and so, you know, the transversality theorem says if you have two submanifolds, then you can isotope one or the other or both to make them transverse. Transverse means that at any point of intersection, the tangent spaces add up to the total space, to the tangent space of the total manifold. It also says that if they already are transverse and you wiggle them a little bit by small isotopy, they remain transverse. So transversality is a stable property. So we can assume they're transverse, and up to small perturbation they will stay transverse. And so the conclusion of that is that we can do dimension counting. We now think about so if, here's, let me just remind you, reminder, if, to count the intersection, the dimension of a transverse intersection, you don't count dimensions, you count codimensions. The mantra, you know, the thing that the mnemonic for me is codimensions add. So if M has codimension this, N has codimension that, then, and they intersect transversely, then the dimension of the intersection is codimension equal to the sum of those two. So let's apply that to this case, and already everything on that board that I want. Well, let's do it here. So codimension of, but remember, we're doing codimension in F inverse of T, not in X. So codimension of A P T is equal to what? So it's equal to n minus 1 minus n minus k minus 1, so it's k. Codimension of PQT equals n minus 1 minus L minus 1 n minus L. So the codimension of the intersection AT intersection T equals n plus k minus L. That's the code. So what's the dimension of it? What I really want to get to is its dimension. Remember that that's the codimension in here. So therefore, the dimension is the dimension of a T intersecting T is the dimension minus the codimension. So it's n minus 1 minus n plus k minus L, which is L minus k minus 1. Sound good? And which one was L and which one was K?
It's Q.
K, yeah, it's alphabetical, right? KL, Q. Okay, so this is index K. This is index L. Okay, so now what does that mean? First of all, if this is negative, they should not intersect. So case 1, intersection equals the empty set if L minus K minus 1 is less than 0, which means that L is less than K plus 1. Okay, so i.e. if L equals L is less than or equal to K. Right? See that right? Yes. So here, L is less than K, or L is actually equal to K. So the point is now, if I have, and that's conclusion. If I attach, so first of all, look at the L less than K thing, right? So if you attach, if index if lower index occurs above higher index, if low index occurs above high index, then in terms of the handle decomposition at least, it doesn't matter that, you don't have a one handle. If an index 1 critical point occurs above an index 2 critical point, well, in terms of handle decomposition, you still might as well attach the one handle first, or at the same time. Handles can be attached at the same time. Because remember, the whole point was, I was saying that if these ascending and descending manifolds are disjoint, then you could consider the two handles to have been attached at the same time. So handles can be attached at the same time. And actually, and then the other thing is handles of the same index can always be attached at the same time. And now, the case 2 is when the next case I'm interested in, the only other case I'm going to think about is when is it 0 dimensional? So dimension equals 0, i.e. A, B, T intersects D, and T points, and L is equal to K equals 1. It could be empty, but it could be points, right? So what's going on there? This is precisely, e.g., K equals 1, L equals 2, right? This is precisely the situation where you have, well, the picture here, for example, would be if I now have a two-handle here, forget about that Q for a moment, just look at this. If this is Q up here, that's index 2, and this is index 1, then the descending manifold here is this disk which then has boundary equal to a circle and intersects at one point, and there's no way you can say that that Q was attached, that handle is attached before you attach the one handle. It necessarily goes over this one handle. So what we do is we say, anyway, in this case we say that, if this intersection is non-trivial, if is not empty, we say that the Q handle, the handle for Q goes over the handle for P. And so that's one example where it goes over. Another, in 3 dimensions, we've seen examples of this already, and so 3 dimensions and 4 dimensions, we've seen examples of, so this case, the example I drew before, where I had this is a 4-dimensional example. This is the Maser manifold. I'm not going to draw the framing for the 2-handle, but there's a 1-handle. So how do you visualize this? You've got to think about the Morse function. You've got this index 0 critical point in the middle of the ball. That's the 0 handle. It expands out. The level sets expand, or a 3-sphere. And then then the level sets encounter these balls and sort of put little fingers up into the 1 handle that's going over here, and then join. And there's a index 1 critical point, and then it splits out. Now the level sets are S1 cross S2, or S1 cross S2s. And now I'm going to attach a 2-handle that goes over 3 times. And crossing, clasp. I'm not drawing the framing, but the point is now, if this is it, then I encounter. Now the level sets get harder to visualize, but they come into this 2-handle, and if I think into your neighborhood of this, go up and meet an index 2 critical point, right? And so that index 2 critical point, its descending manifold, well, what I've drawn here is almost the attaching sphere. This is exactly, so Q equals the index 2 critical point. And P equals the index 1 critical point. Okay. This circle here is exactly the descending manifold for Q intersecting with a certain level set. Okay. And if we imagine we're drawing a picture inside S1 cross S2, where's the ascending, so this is a sphere, right, a sphere of dimension 1, where's the ascending sphere for the index 1 critical point? Well, it's not here yet. It's actually I've got sort of this wormhole that comes through space from this sphere to this sphere, and the one exactly in the middle, that's the ascending manifold for this index 1 critical point, so that's sort of somewhere here in the middle is this ghostly sphere, which is right in the middle of the one handle. And so when these guys go over and intersect it and then keep going, I have 3 points of intersection. Okay, and those 3 points of intersection, in this case, here is the ascending QT, and then in this case, ascending QT intersects ascending from P, descending from Q, is equal to 3 points. But you can think of any of these spheres as being like the ascending manifold for that lower index point, and so there's 3 points of intersection. Okay, that's all well and good. So it is not unreasonable to expect things to intersect. It's also not unreasonable to expect higher dimensional intersections, like if I have things separated by index 2. So if K was 1 and L is 3, you can expect circles, one-dimensional manifolds worth of intersections and so forth. But what I want to do now is think about what happens if we have, so what I'm working towards now is what happens if we vary F and G together. Okay? So what I want to do now is consider one parameter families. For F sub T, G sub T. Okay. But let's keep things simple for the moment. So step 1. Let's just assume F, F sub T is really just F. It's a constant. So we're just going to vary, it's constant in T. So we're really just going to vary the metric and not the function. Shortly we'll vary both. Okay. But just to get started, we've already sort of argued about this already, but what I argued first is that if you fix 1, then generically you can assume that these intersections are transverse. Now I want to say, suppose you have a 1 parameter family, from one to the other, how can you make some sort of similar argument that generically, what I want to argue is that the ascending and descending manifolds are transverse except at isolated times. So claim. So what I'm now, the reason I'm keeping F constant is I want to just focus on just two critical points again, right? So the claim is that, I have a bad thing now, which is I have 2 things called T. And I really wish that was not T. Because this is really, but I guess we'll pull it and call that S. Then the claim is that so I can now take the ascending and descending manifolds and fixed by as T, but I can think of them as also depending upon parameter S. Okay? And then I can look at that and the descending manifold for Q at time S at level T. Okay? And I can these will intersect. So I want to consider now S goes between 0 and 1. claims that these intersect transversely in F inverse of t for all but finitely many values of s, and I want to tell you what happens at those finitely many values of s. But the right way to do it is not to make that, the right way to do it is say that jack everything up one dimension and say that something else is actually intersecting transversely. Okay. Yeah.
So when you say this, are you claiming that every such?
No, I'm sorry. Okay, we can assume. Okay, the claim is after a small
It's like you could like imagine one that lines
right,
up. And
after a small perturbation of the one parameter family of g sub x. So in other words, I'm given some g sub s, and it may be pretty non-generic, but I can now wiggle. I've got a homotopy, and I can wiggle that homotopy. Right? Originally, I took a fixed thing and wiggled it, and got transversality. Now I'm going to go by path of things and wiggle the path. Right? Thanks. So up to a small perturbation of g sub s. But the right way to do this is just to say that actually the same argument we just did will hold, but we're going to count dimensions in a different space. And get the transversality there. Yes. One cross x. And we can then, so, I mean, there's a fancy way to say this, but all I really want to do is the idea is fairly simple. I want to, promote this one parameter family. I basically just think about the vector fields, forget about the metric. I want to promote this one parameter family of vector fields on X to one parameter family of vector field to a fixed vector field on 0, 1 cross X. Okay, so what's so common? We already sort of know that we can, forget about the metric and focus on the vector field. A little bit, again, the metric carries a lot more information than the vector field, but if you isotope the metric, you'll isotope the vector field. If you isotope the vector field, you can find the corresponding isotope of the metric. So then the point is, you get a vector field, the gradient vector field d sub s on x gives some vector field w on 0, 1 cross x, which is just it's just equal to the point is you can have no 0, 1 direction. There's no, if I call this s direction, no d by ds component. So understand what I mean? And on the s cross x slice, it's v sub s. Okay, so that gives you this one parameter family. That gives you the vector field of the whole thing, and then all you want to do, maybe that is sort of taking too big of a thing of a simple idea. I just want to take this single ascending manifold at each time s, I want to take this manifold, and then as I move in time, that manifold moves, and that gives a one-dimensional manifold. So a one higher dimensional manifold. So you get out of all of this, you get some. I don't know what let's use blackboard bold. Blackboard bold A, P, T, okay, which is in 0, 1 cross X. And understand what I'm doing, I'm just taking these A sub P sub S's, A sub PS, and then I'm just extending them by the critical point staying fixed. I'm just as they flow across, as they vary from s goes from 0 to 1, I fit them all together to make a one higher dimensional manifold. So the dimension of this is equal to the dimension of this is equal. It was k dimensional, and now it's equal to 1 dimensional, right? And then d sorry, that's I just want that first without the t. So that's just all the ascending manifolds extending across, and then this is dimension. So it was dimension n minus 1. Sorry, it was dimension n minus l, and now it's n minus l plus 1.
Isn't it still just for a single t, isn't it s that is?
The whole thing is going to move, right? I mean, I could do either one. I'm now going to move. Well, I mean, I'm next thing I'm doing is put the t's in. I mean, the ascending manifolds and descending manifolds move around, and they sweep out something, one high dimensional. Now I'm going to once again intersect with that versus t. So, I mean, I could have done that right away. So then,
K n minus l with the co-dimension, right?
k was the index of. Oh, got it backwards, right? Yeah, ascending higher, n minus k plus 1, l plus 1. Yep. Okay, so now, therefore, put the t's in, we get a t and t in 0, 1 cross t. Right, and then these have dimensions. Dimension equals, I drop the 1 again, n minus k. This has dimension L, and then this has dimension N, and now we want to compute. So the point is, then, by similar argument, we can assume that these submanifolds intersect transversely. Assume. So by a similar argument, so that means we can, if we had an isotopy of these submanifolds inside, well, you want to be a little careful. You want it to be an isotopy that preserves the fact that these submanifolds don't sort of go backwards in time. So it's a time preserved, this is the time direction. You want to take a time preserving isotopy of these things. So you just, that's not a, that's an open condition. So you can move those around, and the point is you can so you can well, I'll let you figure that out, but the same argument we just gave can arrange that these are transverse intersections. And so once you then count codimensions again, so codimension of the sum of the intersection intersecting with qt is the sum of the codimensions here, so now it's just k plus n minus l. Right? Because codimension of this is here is k, codimension of this is n minus l, and therefore the dimension is just equal to k plus n now. Right? And so the point is that there's a minus sign somewhere. K
In
it should be a minus l, minus l, so it's k minus l. I'm taking it's l minus k. I'm taking n minus that. It's l minus k. Okay, so now that's the dimension of this intersection, and so when is it? So if when is it negative? First of all, it's negative if L is less than K. If L is less than K, then the dimension should be a. We expect the intersection to be empty. So what that means is, well. So that means in a one parameter family of metrics, we still never expect, so suppose I have an index 1 critical point and an index 2 critical point, so one handle and a two handle. We know that at a fixed time, the two handle should not go over the one handle. We know that at a fixed time the one handle should not go over the two handle. because it's a lower index. But now it's saying that also in a one parameter family, you would never expect the one handle to go over the two handle. Here's what you might see. So you might think the one handle, well, why doesn't the one handle go up and over the two handle and back down? The point is, if it does, what really going over the two handle is hitting exactly the critical point there. If it hits exactly the critical point, you wiggle it a little bit, it won't hit the critical point, and then it'll flow back down at the bottom. So basically, if it goes, here's the two handle, here's the one handle. If the one handle goes over the two handle, you push it off, and it might as well just go around one side or the other. Although it does raise the interesting point that in a two-parameter family, you can go from going around this side to going around that side in a non-trivial way. So we won't do that right now. But if you now have two time parameters, right, and then do all these arguments again, when L is equal to k minus 1, you can have points of intersection. Okay, but if L equals k, then you might have points. That means at particular times, i.e. At isolated values of S, you have a PS T intersecting ST. So that means if you have, yes. There's also the question of, okay, so, there's one other case that I want to think about. Let's just write this down and then come back to think about this a little bit. If L is equal to if L equals k plus 1, then L minus k is 1, right? And then A sub p, this thing is one-dimensional, okay? Let's just say, let's think about that case later. What it means is this thing is a one-manifold, okay? This thing is going to be a one-manifold in time. Now, one-manifold in time there's two things that can happen. One thing that can happen is you could have, so that means that at a fixed value of S, you have maybe some number of intersections from an index 2, say, down to an index 1, some number of flow lines. And then, as time advances, they could just all stay where they are. Or you could have a different kind of behavior where the one manifold does this, which means two of those intersection points come together. Right? And we'll sort of think about that case as a special case. But let me focus first on the L equals K case. L equals K. What's going on there? Well, here we get handle plots. So I think the best thing is just to illustrate these with examples rather than try to write down a full coordinatized picture of it, right? So let me draw sort of the flat picture first. Let me draw the handle decomposition story first. So suppose I have a 0 handle and a 1 handle, and then another 1 handle. So they're the same index. Let me draw the ascending and descending manifolds for these two. Right, so let's suppose that this is, first of all, where are the critical points? The critical points are right smack in the middle of the handles, right? So this is P, which is the lower one, and this is Q, which is the higher one, right? Let me draw the ascending manifold for P and descending manifold for Q. Descending manifold for Q is this, it comes down here, and goes down, actually in this case it goes all the way, well, depending on how far we want it to go, it actually goes all the way to the index 0 critical point. Right? And then here the ascending manifold for P is just that little thing. And if we cared about a particular level set in between them, where is a particular level set in between them, it's well, I can imagine it's actually a good way to imagine what's going on here is we attach this one handle first. Now here's a level set. And now we attach this, let's sort of thicken everything up. And now we attach this one handle. So the level set in which I'd be interested in the intersection happening might be this level set. This level set here. So here's so this would be F versus T. And I have descending manifold hitting at 2 points, ascending manifold hitting at 2 points, and they're disjoint, right? And now, in time, what can happen is that how is this descending manifold going to intersect this ascending manifold? Well, by an isotopy of this pair of points, where this, let's just isotopy this one, for example. This one is over here, and then suddenly intersects, and then crosses to the other side. Okay, so that's this handle sliding over that handle. So by so I will draw all the details, but you get this, and the intermediate stage, you have this handle coming down here, and so exactly at that time, you have the descending manifold for Q. Part of it keeps going all the way down, right? But part of it runs smack into the ascending manifold for P. And there's your point of intersection. Non-transverse point of intersection, right? 2 points. It's non-transverse at that fixed moment, but if you think about it as something, one higher dimensional phenomenon, it's a transverse intersection. So if you don't think of these 2 points as sweeping out arcs in this F inverse of G cross I, right? They come and they cross and they continue. And another point though is that itself should be a transverse intersection. So you could have a single point of intersection, which is not transverse, where it comes and they come together and they separate like that. And that would mean it sort of starts to slide and then gets right to the point and gives up and goes back down the other side again. And that generically should not happen, right?
Because you could just like
Then you might as well not have done it, right, exactly, right. But, so the key thing is we haven't drawn the whole picture to know that it's really a transverse phenomenon. And so if you keep going, it should pop down the other side. And it's kind of clean again. So I can draw the thing. Okay, so that's the picture, and we will talk a little bit more about what the easiest handle slides to understand are slides involving one handles. The important thing to remember about a handle slide is it occurs between 2 critical points of the same index, and I'm staying, this is as far as I want to go to think about critical points of higher index, but obviously bizarre things can happen if you have, critical points of index separated by index 4, they're in transverse intersection, can be something very complicated, and that can go through some complicated, actually what really happens is that goes through a coordinate. Very precise about it. The actual, in a one parameter family, in general, the intersection of, the point is the intersection of the one, when you cross with 0, 1, then the intersection of ascending and descending manifolds is itself a submanifold, which is a coordinate of the intersection of this end and the intersection of that end. So obviously those can get arbitrarily complicated. What we're using here is the fact that one manifolds are particularly easy to understand, and so is 0 manifolds.
Can I make sure you have this dimension concept? So a non-blackboard script, a
Yeah.
PT is dimension n minus k minus 1.
if I
Is that right?
well,
Well, it's one less than these, right?
It's one less, yeah, and minus, that's right, and yeah, exactly.
Okay,
Yeah.
so that's the definition of the tangent cases. When you sum them, you will always get n minus 2, which is why these intersections are always.
That's right, n minus 2s can never add up to n minus 1. Remember, this is all transversality in f
Yeah,
intersects.
right.
I mean, the point is, in some sense, because everything is, both things are flowing along this fixed vector field, we sort of have to look at things in a slice, because in the other direction, they always sort of have the same tangent direction vertically, and then we have to sort of, that's why we just cut down to sort of slice things. Okay, we're out of time. So, Monday we'll, I think we'll talk about exercises, and then, and remember, if anyone's interested in coming out to dinner with us and Bruce tonight to talk.